All right, so we're going to go on to what are called buffer solutions. Now I want to go back to what we did in the last video with the common ion effect. Remember that we took an acid and we added its conjugate base, and that shifted the equilibrium in this direction. So this was the acid, this is the conjugate base. All right, then we also did one here where this is the base, and we added the conjugate acid, right? So that's going to become important because basically what we're doing with these are we're creating what are called buffer solutions, okay? Buffers are incredibly important. In fact, if it weren't for buffers, you wouldn't be alive, right? Buffers, these chemicals in our blood, keep our pH very stable. They are able to write changes that might occur in our bodies with respect to pH. So life depends on it. It's very, very important. So solutions that contain a weak conjugate acid-base pair are called buffers because they are able to resist drastic changes in pH. And we're going to kind of look at why that is. Now, if you need to assign the solutions that give good buffers, it needs to be a weak acid or base and its conjugate acid or base. So that crosses out that one because that's strong. That crosses out this one because it's strong. Okay, so those automatically aren't going to work. This is a good one. This is a weak acid, and the conjugate base is F minus. Now, that's a weak acid, and that's a weak base, but they're not conjugates. That crosses that out. Now, here's a weak base, and the conjugate acid, which is ammonium. That's a good buffer. This one is a weak acid, and the conjugate base, which is cyanide ion. This is a weak base, and this is a weak acid, but they are not conjugates of each other. But these are. This is a weak acid and its conjugate base, and so that's a buffer as well. So I kind of already did that. So let's look at. We're gonna kind of look at this Ka expression, and we're gonna rearrange it and solve for H plus. So we're gonna say H plus is equal to. Whoops, sorry about that. H plus is equal to Ka times Ha divided by A minus. So all I did was multiply, cross multiply, and I got this. Okay. Now, what this means is that, and I should put concentration of, the concentration of H plus is dependent on the Ka value, and we know that, right? High Kas give you high concentrations of hydrogen ion, we know that. And this ratio of Ha and A minus concentrations, right? This ratio of the concentrations of these two is also important, this and that. So what that means is if I keep these concentrations relatively constant, then this, being a constant, will keep this constant, right? So the initial, if I find a concentration where HF is equal to the concentration of F minus, then that will help that hydrogen ion concentration remain stable. So let's say that I have HF, all right, and I add OH to it. Then I'm going to get F minus plus H2O. So let me go to this picture while I'm doing this so we can kind of see what I'm doing here. So I basically have this initial concentration or solution where HF is equal to F minus. All right. Now, what happens if I go ahead and I add OH to this, right? Then I swing in this direction. Now, this is how I kind of think about it. When I add OH to this, there's a little bit of HF there to pick up that excess, so I get a decrease in HF and an increase in F minus. There it is, right? So when I do this, I add this to the buffer will cause the HF to decrease and F to increase, right? And there it is. F is increasing, this is decreasing. If I add H, however, then the H plus is going to react with the F minus part of this buffer solution, and it's going to make the HF go up a little bit and the F minus go down. Okay, so let's write this out. So I've got H plus F minus goes to HF. And when I add this, it causes HF to increase and the F minus to decrease, but just ever so slightly. Ever so slightly. Okay. As long as this ratio doesn't change very much, the pH change will be small, correct? Because, again, when we look at this equation, this is dependent on either this or this ratio. If this ratio doesn't change much, then that's not going to change much because that's a constant, right? So that means this isn't going to change much. So it's able to stand a change in the concentration. So let's say that we want to find out what the pH of a buffer solution is. Now remember, we're going to use what's called the Henderson-Hasselbalch equation. It's in your reference chart. And this is only used when I have a weak acid or a weak base and its conjugate base or conjugate acid. It's the only time I use this equation. Now, if I took that equation here and I just took the log of everything, the log of this, the log of this, and the log of this, that's all I'm going to do, then I'm going to get that the pH is equal to the pKa plus the log of the base over the acid. Now, really, in your reference chart, this is equal to pKa plus the log of A minus over HA. I think it's kind of better to remember that the base is on top, and you'll see why in a minute. But this is what I've done. So here's a buffer solution. Now, in this one is interesting. It says use the Henderson-Hasselbalch equation to calculate the pH of this solution. Now, a lot of times on the test, they won't say use the Henderson-Hasselbalch equation. They'll just say I have this weak acid and its conjugate base. Here's the Ka. What's the pH? And the reason I know I can do that is because I have the weak acid and its conjugate base. That's a buffer. So that tells me that I can do this. So the pH is equal to the pKa plus the log of the concentration of C2 of the acetate ion, which is the base, divided by acetic acid. Right? And that's equal to the negative log of, so I'm going to take the log of everything so I can get real numbers here, times 10 to the minus 5, right? So that's the pKa, plus the log of 1 over 1. That's going to be equal to 0. So this is equal to 4.74. Okay. Now, what this means is that at this point, because this is 1 over 1, the pH is equal to the pKa. So when these concentrations are the same, and this ratio is 1, then my pH is equal to pKa. But what happens when it's not 1? Notice here I have a little more acid and a little less base. So I should have more acid. So in comparison to 4.74, this pH value should be lower. In this case, I have a little more base. So in this case, my pH should be higher. Let's see if this is so. Okay. I'm going to go down here. I'm going to call this 1 and this 2. And I'm going to do these down in this empty space here. And I'm going to kind of write small. So let's just plug and chug. pH is equal to pKa plus the log of C2H3O2 minus divided by C2H3O2H. That's equal to the negative log of 1.8 times 10 to the minus 5 plus the log of 0.8 divided by 1.0. That's equal to 4.74 plus a negative 0.097, and that's equal to 4.64. Look at that. There's more acid, so it actually caused this to go down, but not by much. Let's look at number 2. Number 2, I'm going to plug everything in the same. This is going to be negative log of 1.8 times 10 to the minus 5 plus the log of, this time it's 1.0 divided by 0.8. That's equal to 4.74 plus 0.097. Box that. And that's equal to 4.84. Sure enough, it did go up, didn't it? Because it's a slightly more basic, but not by much. And so I had this swing in concentration, but my calculated pH value did not change significantly. I can do the same with a base. I can calculate, use a base here. The pKa of the ammonium ion is 9.25. I just took the negative log of this. The pH of the solution is 9.45, which is greater than the pKa for this. Therefore, the solution must contain more base, which is this, than that. Because my pH is higher than what it normally would be, my pKa. And so that means I have a little base in there. So let's calculate that. The pH is equal to pKa plus the log of NH3 over NH4 plus. Now in this case, I've got, this is going to be 9.43 is equal to 9.25 plus the log of ammonia divided by 0.8. When I do this, I get 0.18 is equal to the log of ammonia divided by 0.8. And then I do that math. I take the inverse log of both sides, and I get ammonia divided by 0.80, and that turns out to be NH3 is equal to 1.2 molar. And so when I actually do that, the 1.2 molar, that gave me the concentration of the ammonia, knowing this and the pH, which is here, I can calculate one or another of these. But I need to remember that I've got it when I go from here to here, I've got to take the